Elimination reactions, the Baeyer test, and experiment notes. In this webcast, we will discuss the chemical reaction aspects of the unimolecular elimination experiment. In the previous experiment, you performed a unimolecular nucleophilic substitution reaction. You know from Chem 232 that substitution and elimination reactions are often in competition with each other. Let us begin this webcast by discussing that topic. From Chem 232, you know that whenever you have the conditions for an elimination reaction, you also have the conditions for a substitution reaction. Where if we have a substrate such as this, where our leaving group is in blue, in the presence of a nucleophile, we can have a substitution reaction where our leaving group is substituted with the nucleophile, this top pathway, leading to this product, or our nucleophile can instead act as a base, deprotonate this red hydrogen here, leading to this bottom pathway, and the formation of an alkene product. This is an unfortunate reality. If we want a substitution, we always have to worry about elimination. And if we want elimination, we always have to worry about substitution. Fortunately, there are things that we can do to bias one pathway, one reaction over another. For example, substitution reactions can be encouraged using strong nucleophiles that are also weak bases. Examples include the chloride ion and the bromide ion. If we want an elimination reaction to occur, we can encourage that using weak nucleophiles that are strong bases. The tert butoxide ion is an example of this type of base. If we use a strong nucleophile that is also a strong base, we can and will make a mixture of substitution and elimination products, the amount of each depending on the type of leaving group present, whether it is primary, secondary, or tertiary. Why do particular reaction conditions result in particular reaction pathways being preferred? To answer that question, let's limit our analysis to only SN1 and E1 reactions. Let us assume that we have reaction conditions where we know we are going to go through a carbocation like we see on this slide. We have a substrate over here in the presence of a nucleophile. This substrate is going to form a carbocation, which can then go on to either the substitution product, the top pathway, or the elimination product via the bottom pathway. What determines which pathway is preferred is the transition state leading to those products. To discuss that, let us draw a reaction coordinate diagram. Remember that a reaction coordinate diagram is essentially a graph showing the progress of a reaction. Our reaction starts with our substrate and our nucleophile at some energy. We then form this carbocation, which we know is a high energy intermediate. So we go from our starting energy to our carbocation. Now we have a choice. We can form either the substitution product or the elimination product. Let's go ahead and draw those pathways here. The substitution product will be shown by this blue curve, and the elimination product will be shown by this red curve. Some product at the bottom for substitution, and some product at the bottom here for elimination. You know that in order to go from one part of a reaction coordinate diagram to another, we have to pass through this transition state here at the top of the curve. And that means we need enough energy to go from our starting position here, in this case our carbocation, to get over this hump. Based on that knowledge, you can see that it takes less energy to go over this red curve, leading to the elimination product, than it does to go over this blue curve, leading to the substitution product. Because it takes less energy to go over the red hump, the elimination reaction is faster. Therefore, the elimination product would be the major product based on this reaction coordinate diagram. Notice how the elimination product is higher in energy than the substitution product. The elimination product is less stable than the substitution product. That is completely irrelevant when determining which product is the major product. One note before we continue. This assumes that these reactions are irreversible, meaning that once we make product, we can never go back to starting material. Because substitution reactions and elimination reactions are generally irreversible, it is the transition state energies that determine which product is the major product. By choosing different reaction conditions, we alter the height of these transition state energies to make sure that our desired product is the major product. Now let us apply that knowledge to predicting the products of an elimination reaction. In Chem 232, you were taught Zaitsev's rule. Zaitsev's rule states that the more substituted a double bond is, the more stable it is. Furthermore, in an elimination reaction, the most stable possible alkene should be the major product. Let's show an example. Let's take this alkyl bromide and perform an elimination reaction. If we do that, we would get a mixture of products. On the left, we have this terminal alkene. In the middle, we have this disubstituted trans alkene. And on the right, we have this disubstituted cis alkene. The terminal alkene is formed from a base deprotonating one of these hydrogen atoms at the end of the molecule. In this case, we're showing an E2 mechanism, where the carbon-carbon double bond is formed simultaneously as the leaving group is kicked out. The cis and the trans double bond are formed in a similar manner, just using hydrogen atoms on the other side of the leaving group, shown here in red. According to Zaitsev's rule, the more substituted a double bond is, the more stable it is. Therefore, either the trans or the cis double bond should be the most stable, because they are disubstituted, whereas the terminal alkene is only monosubstituted. You know from Chem 232 that the trans alkene is more stable than the cis alkene because there are fewer steric interactions between the substituents. Being on opposite sides of the double bond is less crowded than being on the same side of the double bond. Therefore, the trans alkene should be the major product, it should be the one that's produced the most, and the terminal alkene should be the minor product, the product that is produced the least, with the cis alkene somewhere in the middle. But on the previous slide, I told you that the stability of the product has no bearing on what the major product should be. Why is it that in organic chemistry we teach you this rule? This is because there's no way for you to look at a compound and say, yeah, the transition state that leads to this compound will be lower in energy. Fortunately for us, in most cases, for an elimination reaction, the most stable product happens to result from the transition state that is lowest in energy. This is also why using bulky bases can change the product distribution. You know that using tert butoxide, a bulky base, you would make primarily the terminal alkene, even though it is less stable. This is because by using the bulky base, you alter the transition state energies to make the transition state leading to the terminal alkene product lower in energy than the transition state leading to the other products. Now that we have talked about transition states, let's talk about the E1 mechanism. In this experiment, you'll be taking cyclohexanol, shown here on the left, and treating it with phosphoric acid, which is a strong acid. Like in the SN1 experiment, you'll be protonating this alcohol to turn it into a good leaving group. Similar to what was stated in the mechanism discussion in the SN1 webcast, this protonation step is not part of the E1 mechanism proper. This protonation step is to get the molecule ready to undergo the E1 mechanism, but is not part of the E1 mechanism itself. Once you have made this good leaving group, you will then allow it time and energy through the use of heat to form a carbocation, which will then be deprotonated using a base of some kind to form the alkene product. Before we move on, to be clear, the E1 mechanism is a two-step mechanism that consists of the formation of a carbocation, shown here at the bottom, and the subsequent deprotonation of a hydrogen atom adjacent to the carbocation, as shown here on the right. Remember, the initial protonation step is not part of the E1 mechanism. The protonation step prepares the molecule to undergo the E1 mechanism, which consists of the leaving group leaving to form the carbocation, and the subsequent deprotonation to form the new alkene. A simple mechanism and very similar to the SN1 mechanism in the previous experiment. Both reactions go through a carbocation. The reason that we go through an elimination reaction here instead of a substitution reaction is because we do not have a good nucleophile. In the substitution experiment, you produced a chloride ion, which is a fantastic nucleophile. In this experiment, you're forming this dihydrogen phosphate ion, which is a terrible nucleophile. Because it is a terrible nucleophile, any substitution reaction is slow, which gives enough time for something, either the dihydrogen phosphate ion or the solvent or some other base, to come along and deprotonate the hydrogen to form the alkene product. One final note about this mechanism before we continue. As you might have noticed, this reaction is catalytic in acid. We start with an acid, and then we regenerate that acid over the course of the reaction. Keep this in mind for when you fill out your table of chemicals in your pre-lab notebook. The phosphoric acid will not be the limiting reagent, even though it is the reagent that would appear to provide the least amount of product. This is because the acid is not consumed over the course of the reaction. Because the acid gets regenerated, it cannot be the limiting reagent. When you're filling out your table of chemicals, do not set the equivalence of acid to 1, even though it may be the reagent with the fewest number of moles. Instead, you should set the number of equivalents of the alcohol to 1, and then set all of your ratios based off of that. This may mean that you have fewer than 1 equivalent of acid. That's okay, because it is catalytic. The reaction component of this experiment is pretty simple. You will take some cyclohexanol and you will add it to a round-bottom flask. You will then add some phosphoric acid to that flask to start the reaction. While the reaction is running, you will simultaneously be fractionally distilling the cyclohexene as it is formed. After you have collected the cyclohexene, you will then dry it using potassium carbonate. To separate your product from the potassium carbonate, you will then perform a simple distillation, and then, if necessary, dry your product again, and finally, perform something called the Baeyer test to confirm that your collected liquid is in fact your product. The purpose of the Baeyer test is to determine if there is unsaturation, or in other words alkenes, in your final product. How the Baeyer test works is you will take a sample of your compound, hopefully containing an alkene of some kind. You will then add a solution of potassium permanganate, which is purple in color. If an alkene is present, it will react with the potassium permanganate to form a diol. This will have 2 consequences. First, the solution will go from purple to colorless. As the potassium permanganate is used up, the purple color goes away. The second consequence is the formation of solid manganese dioxide, which is a brown solid. What you will do is you will take this potassium permanganate solution and add it to a solution of your product and your starting material. If you see a brown solid after testing the solution of your product, you have a positive test for unsaturation, or in other words, you have an alkene in your product. Now sometimes you may not see any brown precipitate form. This is why we add potassium permanganate to both the product and a solution of starting material. What this allows us to do is to compare the number of drops it takes for the solutions to remain purple. If your starting material takes 1 drop to remain purple, but your product takes 10 drops to remain purple, even if you don't see any brown solid, that tells me that your product contains alkene. It took more drops to remain purple, that means there was alkene in there to consume the potassium permanganate you are adding. That brings us to the end of this webcast. To recap, if multiple reaction pathways are possible and they are irreversible, then the pathway with the lowest energy transition state leads to the major product. The energy of the products themselves is irrelevant. Whichever product is easier to make, requires less energy to make, will be the major product, even if that product is not the most stable of the possible products. The Baeyer test confirms the presence of alkenes by reacting potassium permanganate with any alkenes present in the molecule. If there are alkenes present in the molecule, then this reaction will produce a brown precipitate and/or a difference in the number of drops needed to maintain the purple color change that results from adding potassium permanganate. If it takes more drops of potassium permanganate to keep the solution of your product purple than it does to keep a solution of your starting material purple, then your product likely contains alkenes.